Hi everyone! Today we'll be taking a journey into the vectors to the stars, where we will delve into Kepler's laws of planetary motion and see how multivariable calculus plays a part. Kepler's laws describe the motion of objects in orbit of a huge object, which can be visualized through the motion of planets in the solar system. To put this simply, Kepler formulated three laws. The first law states that planets orbit the Sun in the shape of an elliptical orbit. The second law states that a planet will cover equal areas of space in equal time periods. The third law states that a planet's orbital period squared is proportional to the size of its semi-major axis cubed.
Kepler's laws were named after their creator, Johannes Kepler, a German astronomer. In 1600, Kepler met Tycho Brahe, a Danish mathematician and astronomer who was collecting, for the time, highly precise data on the movement of Mars. He spent a year as Brahe's assistant in Prague, working with him to collect and analyze Brahe's highly secretive data. Following Brahe's death in 1601, with access to the full breadth of Brahe's precise data, Kepler first published Astronomia Nova in 1609, containing his first and second laws of planetary motion, explaining the motion of Mars. 10 years later, Kepler published Harmonice Mundi, which contained his third law. In the years that followed, Kepler built on his findings to publish further, analyzing and building on the heliocentric model, publishing the Rudolphine tables, a collection of data and calculations used to predict planetary positions. While not his first discovery, the basis of the many other laws is based on the first law, that the orbits of planets are elliptical. While Kepler determined this from observations, this can be proven using modern calculus. First, let us assume that all planets move in an orbit given by the vector-valued function r vector. Let r equal the magnitude of r vector given a specific time, g equals the universal gravitational constant, big M equals the mass of the Sun, and little m the mass of the planet. Here, we bring in Newton's laws. Newton's second law of motion, force equals mass times acceleration, and Newton's universal law of gravitation, force equals negative gmm over r cubed times r vector. Since they are both equal to force, we can set them equal to each other. Since little m is on both sides of the equation, they cancel each other, and we are left with acceleration vector equals negative gm over r cubed times r vector. At any given specific time, since minus gm over r cubed is constant, so r vector is a constant multiple of a vector. Thus, we can say they are parallel. On another track, the quantity of angular momentum is expressed by the L vector, and is equal to r cross the velocity vector, or r cross r prime. Here we see the derivative of the L vector, which is r cross r prime, which, according to the product rule, expands out as seen. We know that the cross product of the same vector equals 0, so r prime cross r prime is 0. We also know that since r double prime is equal to the acceleration vector, and r and acceleration are parallel, the cross product is also equal to 0. Thus, the derivative is going to equal 0, and L is a constant vector. Thus, we can say that r prime moves in a fixed plane, because the normal vector, i.e. the L vector to the plane, is constant. Now that we've proven that our vector moves in a fixed plane, we are now going to move on to a different quantifying factor of the orbit, the eccentricity vector, which is defined by W.R. Hamilton, as seen on the screen. So the eccentricity vector is the vector that points from the center of the orbit towards the periapse, which is a specific point on the orbit. We find the derivative of the eccentricity vector, defined as r prime cross L over gm minus r over r. We can separate this into two derivatives for the first and second term. In the first term, we can pull out 1 over gm and simply find d dt of r prime cross L. Using the product rule, we get r prime cross L prime plus r double prime cross L. We know that L prime is the derivative of L, which we proved equals 0, so the first part goes to 0. Then, we know that r double prime equals the acceleration vector, so we substitute the earlier derivation of a vector. We also know that L vector equals r cross r prime, so we substitute that. After some rearranging, we get that the derivative of the first term, excluding the constant originally extracted, equals gm over r cubed times r cross r prime cross r. The derivative of the second term, r vector over r, can be proven to be equal to 1 over r cubed times r cross r prime cross r. When we plug everything back into the original derivative, we see that the constants, gm, cancel in the first term, and the two terms also cancel each other out. Thus, the derivative of the eccentricity vector is also 0. The eccentricity constant, E, is thus a constant that can be proven to be between 0 and 1. The true anomaly, f of t, is the angle between r vector and e vector. The cosine of that angle is equal to r dot e over re. Now, by rearranging the eccentricity vector, we eventually get gm r dot e equals L squared minus gmr. By rearranging the true anomaly, we get r dot e equals re cosine f of t. Substituting this into the rearranged eccentricity vector, we get gm re cosine ft equals L squared minus gmr. We can rearrange this to state r equals L squared over gm all over 1 plus e cosine f of t. Given that r equals ed over 1 plus cosine theta is the polar form of an ellipse, we can prove that the path of the vector-valued function r of t is an elliptical and the object's orbit is an ellipse. Kepler's first law is the foundation of much of modern-day astronomy and the mathematics and physics of orbits, a field known as orbital mechanics. The accurate prediction of the positions of orbiting objects and other laws, theorems, and axioms in astronomy and orbital mechanics are formed on the basis of Kepler's first law, and elliptical orbits is proved.
So Kepler's second law of planetary motion states that each planet orbits the Sun, and an imaginary line that is drawn between the Sun and the planet sweeps out equal areas in equal time periods. First, we are given that angular momentum is conserved. Since there is conservation of angular momentum, which is denoted by the L vector, and r cross v must be constant, as L vector equals r cross v. This was proved previously in the derivation of Kepler's first law. We will be using this information later in the proof. So coming back to the idea of a planet covering equal areas in equal time periods, we have this diagram. Over a small time period dt, the planet has moved a very small displacement, denoted by dr. Using this diagram, we were able to find equations for velocity and change in area. First, we know that velocity is equal to the derivative of the r vector with respect to time. We can rearrange this equation, which will leave us with displacement dr equals v times dt. With these equations, we can solve for dA. dA is the shape of half of a parallelogram. The area of a parallelogram is r cross displacement dr, so dA is equal to 1/2 times r cross displacement dr. Right before this step, we found that displacement dr equals v times dt. We can plug this into the dA equation, which will leave us with dA equals 1/2 times r cross v dt. Since dt is a scalar quantity, we can remove it from the cross product and divide it to the other side. This leaves us with a derivative with respect to time of the area swept out by the planet is equal to 1/2 times r cross v. Earlier, we proved that the cross product of r and v is constant. Therefore, the area swept out by a planet will also be constant, or the same, for equal periods of time. The practical application of this law is that we realize that as a planet moves closer to the Sun, its velocity increases to compensate for the shorter radius to fulfill Kepler's second law. This can be applied to all orbiting objects, even spacecrafts that receive gravitational slingshots. Kepler's third law states that the square of any planet's orbital period is proportional to the cube of a semi-major axis of the elliptical orbit. To prove this law in the easiest way, we have to initially assume that the orbit is circular. Since we proved earlier that the orbits are elliptical and observationally know that they are nearly circular, this is a fair assumption. These following variables will be used in the proof. ms will be the mass of the Sun, mp will be the mass of the planet, g is the universal gravitational constant, and r is the orbital radius. So, if we focus on the forces of any planet in orbit, we find that there is only one force acting on it, which is the force of gravity from the Sun. This force points inwards, so using Newton's second law, we can write that the gravitational force equals the mass of the planet times the centripetal acceleration. Given that centripetal acceleration equals the orbital radius times angular speed squared, we can substitute centripetal acceleration in the equation, which leaves us with gravitational force equals the mass of the planet times the orbital radius times the angular speed squared. Given Newton's law of universal gravitation, we can substitute it into the equation. This will result in g times the mass of the Sun times the mass of the planet, all divided by the orbital radius squared, equals the mass of the orbital radius times the angular speed squared. We can simplify this equation by dividing both sides of the equation by the mass of the planet, which shows that the mass of the planet does not affect the planet's orbital period. We can also multiply both sides by the orbital radius squared, leaving us with g times the mass of the Sun equals the orbital radius cubed times the angular speed squared. Given the equation for angular velocity, which is change in angular position over change in time, we can find the equation for an entire revolution around the Sun, which is 2 pi over 1 full period, denoted by big T. With this, we can substitute angular velocity and end up with g times the mass of the Sun equals the orbital radius cubed times the quantity 4 pi squared divided by period squared. After rearranging this equation, we get period squared equals the quantity 4 pi squared all over g times the mass of the Sun, quantity closed, times the orbital radius cubed. Therefore, we find that period squared is proportional to the radius cubed, meaning the time a planet takes to orbit the Sun is proportional to the magnitude of the radius vector from the Sun to the planet. This law is heavily used to predict the positions of planets and celestial objects, using their orbital periods and distances to calculate mass and other astronomical quantities.
Kepler's laws are essential in understanding orbits and form the basis of planetary motion, as they were the first calculations that supported the connection between planets. Kepler's three laws of planetary motion also established the heliocentric model for the solar system, with modifications, as the most accurate model of the solar system. This model has largely been the basis for modern solar system models, essential for understanding the planetary orbits vital for interplanetary and extraterrestrial missions. Many of the missions which we undertake today and the technology which we possess would be impossible without the orbital mechanics that we understand based on Kepler's laws of planetary motion. This has been Pranav Shankar.
And Angelina Lee.
Thank you for watching Vectors to the Stars.
Bye!